All right, welcome back. Today we're looking at trig equations. So we're getting into the solving stuff. So we're combining our algebra with our trig concepts. It's a lot to remember, but the more you do of this, the better you get. So let's get into it. So the example says solve the equation, give general formula, and list six solutions. So general formula, we're going to be talking about that as we go through this. And then we're asked to do 6 solutions. All right, so change colors here. So it's asking us solve cosine theta equals 1/2. All right, so this is pretty easy. What we're going to do is we're going to take we want to get to theta, right? We want to solve it for our variable. The cosine is not the variable, the theta is the variable, the cosine is just a function of that variable. So we're going to undo cosine by doing the cosine inverse. I should have left more room on the right side, so let me do that now. So what I do to the left side, I got to also do to the right side. So I'm doing cosine inverse of 1/2. Alright, so on this side, what happens is cosine inverse undoes the cosine. We're just left with theta. So we're looking at cosine inverse of 1/2. Well, cosine inverse of 1/2, just to remind ourselves, is asking us where is the cosine equal to 1/2. So for what theta is cosine equal to 1/2? If we review our unit circle, cosine is 1/2 in quadrant 1. And cosine is also equal to 1/2 in quadrant 4. Right, because the cosine is adjacent over the hypotenuse. Both of these triangles would have a positive adjacent side, and hypotenuse is always positive. So furthermore, we're going to find that the cosine is going to be 1/2 at pi over 3, and then again at 5 pi over 3. Okay, so we're going to list these two. Solutions right now. So we have pi over 3 and 5 pi over 3. So we should expect for there to be 2 places in one revolution of the unit circle where we'd have a solution to this problem. Now it says list 6 solutions. So what we know is that every time we go one whole time around this unit circle, we're going to end up back to where we began. So if we start at pi over 3, we go one revolution around there, then we're going to get another solution. So the general formula here is going to be pi over 3 plus 2 pi. And we're going to say k, where k is any constant. So if I put a 1 in there, then I'm going to add 2 pi times 1, which is 2 pi. If I put a 2 in there, then I'm going to do 2 pi times 2, meaning 2 times around the circle, and that'll give us 4 pi, and so on and so forth. So that would be the general formula for the first part. We have to make sure we do it for the second part as well. And all you have to do is add that 2 pi k, which again just means that every time we go one time around the unit circle, we're going to be back at another solution. Alright, and it says list 6 solutions, so let's do this the easy way. So let's do pi over 3 plus 2 pi. Pi over 3 plus, if I make that a 2, then we have 2 times 2, which is 4 pi. Alright, so any multiple of 2 pi, we're going to have another solution there. So pi over 3 plus 6 pi. And we could also do the same for this solution, right? So we could say 5 pi over 3 plus 2 pi, 5 pi over 3 plus 4 pi, 5 pi over 3, and we could say any multiple, right? Like, so we don't have to list the 6 pi. We could even say plus 100 pi, right? Because 100 is a multiple of 2 pi. So all it's trying to show us is that when we're talking about solutions to these trig equations, we don't only have one solution. We can have infinitely many solutions, and the reason why is because our trig functions are cyclical. They're periodic. They repeat themselves over and over again infinitely. Right, so we're going to find the same answers come up over and over again. So they just want to illustrate that to you. It's not super important going forward into calculus, but if you guys are going to use these ideas for engineering and stuff like that, then I'm sure you will come up with it again when you get to college. All right, next problem. This one's a little different. It's just things to solve and find the answers between 0 and 2 pi. So we like it when they ask us to do this because then it limits the amount of problems that we got to do, or the amount of solutions we have to find. All right, so algebraically speaking, again, we're just trying to get to pi to our theta. We're going to work in reverse order of our order of operations. Right, we said that if we are simplifying, we go from top to bottom, but if we're solving, we're going in reverse order in general. So let's just jump into it. We're going to subtract the square root of 3. We're going to get rid of our, so we did our addition and subtraction. We're looking at multiplication and division now. We're dividing by 2. Notice that we have negative square root of 3 over 2, which is on our unit circle already, so we're kind of headed in a pretty good direction here. And then the last step is we're going to undo our sign by taking the sign inverse. So theta equals sine inverse negative square root of 3 over 2. Alright, so that algebraic part should be pretty straightforward. Now, what we're going to do from here is we're going to figure out, okay, for what angles is sine going to be negative square root of 3 over 2. So, well, I know in quadrant 3 I'm going to have a negative sign, and quadrant 4 I'm going to have also a negative sign. So our sign is going to be negative square root of 3 over 2 at, it's going to be 1 pi over 3, 4 pi over 3, and at 5 pi over 3. Alright, so we don't have to go and do that whole thing about cycling around because they're only asking us between 0 and 2 pi what are our solutions. Our solutions are 4 pi over 3 and 5 pi over 3. If we went any more times around, it wouldn't be within the boundaries that they're asking us to look. So right now they're just asking us to look within one rotation of the unit circle. Okay, so those ones are a little bit easier than the ones from before. Okay, last one. It's asking us to solve tangent squared equals 1 over square root of 3. This one's actually easy algebraically. Now, the thing that I wanted to note is that anytime you have tangent squared, sine squared, cosine squared, secant squared, all that really means, and they write it in a fancy way because they don't want you to think that the theta is squared. All it means is that we're taking the tangent and squaring the whole thing. So this notation, and this is very important, especially when you get into solving and doing identity stuff, and also in calculus, is that these two things mean the same thing. So when we're solving this, all we really have to do is take the square root of both sides. Now the square root of 1 is 1. The square root of 3 is just square root of 3. It doesn't have a square root. And we're going to leave this for now, and I'm going to show you why. But then we do our tangent inverse of this thing, right? So we get theta equals Now, the reason we did this is we're looking at the tangent's weird, the cotangent's weird, so we don't have 1 over square root of 3 on our unit circle. And the reason is because the tangent is actually the combination of the y divided by the x, right? So we don't have just those numbers on it because we have simplified versions of it. And on the unit circle, we only have y's and x's. So here's a hint. Anytime we have square root of 3 and 1 going on with our tangent, what we can do is we can divide by 2 top and bottom. Right, so when working with tangent, feel free to do it. If we have, well, you can do it anytime. If we divide the top and bottom by square root of 2, it's not going to change the value here. So it's just a trick. It's a little shortcut, but you guys would get there anyway if we did the long way. It's not really worth talking about. But again, so we noticed that we had our fraction here. We're dealing with a tangent. We can divide by 2. So we're looking for on our unit circle where the y is a half and the x is square root of 3 over 2. And then it comes out to be positive, right? Because we have a positive tangent. So notice there's actually 2 places where it's going to be. We have one time in quadrant 1 where they're both going to be positive, which ends up with a positive tangent, but also in quadrant 3 because we have the double negatives here, and negative divided by negative is going to also end up becoming positive. So those would be at pi over 6 and at 7 pi over 6. 7 pi over 6. Okay, and we're just grabbing those values from the unit circle. So again, the key here is we're going to, well, there's a few things to note here, right? So 1, anytime we have that square, right, tangent squared, sine squared, cosine squared, any of the trig functions squared, all it really means is that we're taking one of them times by itself, right? So it's like we can put it in parentheses with the square on it. That will help us to remember, okay, to solve this, all I have to do is square root both sides, right? So then we simplified here after solving, and then we said that the trick is, if we're looking at tangents and cotangents, if we have a fraction there, we can divide by 2. So we divided by 2 on top and bottom. And then we're looking for the x's and y's from our unit circle. And we're looking where the y is 1/2 and the x is radical 3 over 2. And again, anytime we have one of these solving problems, we'd expect to have 2 answers between, and I should probably say this too, right, between 0 and 2 pi. And it gets more complicated once they start messing with the thetas. If it's like 2 theta or 3 theta or half theta, like you get more and more solutions within 0 to 2 pi. But I decided to cut that out because we don't have a lot of time and it's not really that important right now. We just want to get into the mode of knowing how to solve these problems, what steps to do to get there. Okay, that's it. So make sure that you have your questions written down. If we need to talk about it, please show up to class and we can discuss it next class. All right, good job today.